Welcome to the Bridging Borders Baltic Hackathon 2024. My name is Kira, and I'm an AI prototype of the Lübeck University of Applied Sciences. I'm excited to be here today to talk about a fascinating topic that is gaining popularity in various industries: chatbots. In this screencast, we're going to explore how to build a chatbot in Python. Chatbots have become an integral part of our lives, from customer service to healthcare to entertainment. They've revolutionized the way we interact with machines, making it more conversational and human-like. But you can also use chatbots in other areas, such as teaching assistants or just to spread good or bad news. And Python, as a popular programming language, has become a first choice for chatbot development. With Python's wide range of libraries and frameworks, building a chatbot is relatively easy and straightforward. And that's what we're going to explore today: how to use the power of Python to build a chatbot that can converse with humans in a natural and intelligent way. If you give me 30 minutes of your time, I'll explain how you can build a language model-based chatbot with less than 30 lines of code. So let's get started. A chatbot is a computer program designed to simulate conversation with human users, either via text or voice interactions. The term chatbot was coined in the 1990s, derived from the words chat and robot. Since then, chatbots have evolved significantly, and today they are an integral part of our digital lives, appearing in various formats and applications. So chatbots are basically computer programs designed to simulate conversation with human users. They can take many forms, including text, voice, or visual interfaces, but we're going to focus on text-based interfaces. The primary goal of a chatbot is to provide automated support via a natural language-based interface, making it seem like you're having a conversation with a human. We've all experienced examples of chatbots in action, such as Siri, Alexa, Google Assistant, or ChatGPT. These technologies have changed the way we interact with devices and access information. Chatbots have become an integral part of our digital landscape, but did you know that there are different types? First, there are rule-based chatbots, which use predefined rules to respond to user input. Then there are AI-based chatbots, which use machine learning to learn from previous interactions or mimic natural language, using more and more often so-called large language models. Finally, hybrid chatbots combine the best of both approaches. Chatbots are no longer simple programs, but sophisticated tools that can simulate human-like conversations, with endless applications in customer service, language translation, and more. As we explore the vast potential of chatbots, it's fascinating to see how they're being utilized across various industries. Chatbots are being used to improve efficiency and customer experience. In customer service, they answer frequent questions and route customers to human support, while in healthcare, they schedule appointments and provide medical information, freeing up professionals for more critical tasks. In e-commerce, chatbots offer personalized product recommendations and assist with checkout processes. And in education, they provide student support and learning guidance, making resources more accessible. Examples of successful chatbot implementations include Amtrak's ticket booking chatbot and Domino's pizza ordering chatbot, demonstrating the potential of chatbots to drive innovation and improvement. More and more often, chatbots make use of a technology that is called large language model. So let us continue our journey investigating what large language models are and how they work, including the architecture behind them. I'll also explain some terminology like prompts and tokens, which are essential components in the text generation process used by chatbots. And finally, I will provide some examples of applications where LLMs are being used, such as text generation, language translation, and chatbots, showcasing the potential and power of these models. A large language model is a type of artificial neural network designed to process and understand human language. These models are trained on vast amounts of text data and can generate human-like language outputs. They are a key technology driving many AI applications, including language translation, dialogue generation, question answering, text classification, and many more. We are seeing new applications emerge every day. LLMs have the potential to revolutionize the way we interact with machines and with each other, and I'm excited to share more about this technology with you. The transformer architecture is very often used for large language models and a type of neural network that uses self-attention mechanisms to process input sequences in parallel. It consists of an encoder, decoder, and self-attention layers that allow the model to weigh the importance of different parts of the input sequence simultaneously. This architecture enables the model to compute a representation of the input that takes into account its semantic relationships, making it particularly useful for natural language processing tasks like machine translation, question answering, text classification, and much more. A language model is essentially a program that converts input text into output text based on learned grammatical and syntactic formation rules. When trained on enormous amounts of data, language models can develop a kind of general knowledge through a side effect of their training process. Therefore, language models appear intelligent. Whether they really are depends a bit on the definition of intelligence one applies, but that would quickly become philosophical and lead too far. Most modern large language models have been trained on a massive dataset of text, which allows them to understand the patterns and rules of language. When a large language model encounters an incomplete sentence, it tries to find the words that are most frequently associated with the rest of the sentence. In our example, the start of a sentence, Paris is called the prompt. The prompt is the text input that the large language model is trained to complete. To do this completion, the large language model divides the prompt into tokens, which are basic units of text. Tokens can be words, parts of words, or even characters. In our example, the tokens could be Paris, is, and the. When the large language model tries to complete the sentence, it generates a new token that follows already known tokens. This new token is chosen based on the probability that it is associated with the rest of the sentence. If the next token would be the word capital, then a likely text completion would be Paris is the capital of France. However, if the next token would be the word city, then a likely text completion would be Paris is the city of love. And if the next token would be the word host, then a likely text completion would be Paris is the host city of the Olympic Games. And of course, there are many more ways to continue the sequence of tokens Paris, is, the, beyond the three examples shown here. The large language model chooses the most probable token based on its training and knowledge of language. It can also generate multiple completion possibilities and rank them by probability. In summary, text completion of a large language model works by dividing the prompt into tokens, generating new tokens to complete the sentence, and choosing the most probable token based on its probability of occurrence. Tokens and embedding are fundamental concepts in large language models. A token is the smallest unit of language input that is individually processed. Tokens can be words, characters, or subwords and form the basis for understanding and generating human language. By processing tokens, LLMs can uncover patterns, relationships, and context to perform tasks such as text generation and language translation. An embedding is a numerical representation of a token in a vector space that reflects its meaning and context. An embedding allows a token to be represented in a numerical vector space so that its meaning and the context in which it occurs are taken into account. This enables the capture of semantic relationships between tokens and enables semantic calculation with the vectors. An example of embeddings are the word representations of the words king, woman, and queen. These can be expressed as vectors, as shown on the right side, and they can be used for calculations. This example shows that with embeddings, one is able to capture semantic relationships between concepts like king, queen, and woman, and thus calculate with them. For example, queen can be expressed as the addition of the embedding vectors of king and woman. At the heart of any large language model lies the concept of a prompt, which is essentially the input text given to an LLM to generate a response. Prompts can be simple questions, sentences, or even entire paragraphs, and they play a crucial role in determining the output of the model. Another important aspect to consider is the context window size, which refers to the number of tokens an LLM can process and consider simultaneously while generating text. It's essential to ensure that the prompt and the generated output fit into this context window size to get accurate and coherent results. Let's take a look at an example to illustrate this. Imagine we want to translate a sentence from German to English using an LLM. The prompt would be the original text along with the instruction to translate it. The generated response would then be the translation of this sentence. As we can see, the prompt is a simple instruction followed by the original text, and the generated response is the translated text. We could also give other instructions, such as rewriting the text to optimize readability, or explaining it in a way that a 5-year-old would understand. Text generation inference is the process that enables trained language models to produce new, coherent, and context-specific text based on a given prompt, input, or context. But what influences the text completion process of these language models? Well, it's not just the prompt. There are several crucial inference parameters that come into play. One of these parameters is temperature, which controls the creativity of the model. By adjusting the temperature value, we can balance between unique and varied suggestions on one hand and safer but more predictable suggestions on the other. Another important parameter is top P, which determines how many of the most likely suggestions should be considered. By increasing the top P value, we can include more suggestions in the evaluation. Max tokens is also a critical parameter, as it limits the maximum length of the generated text in terms of the number of tokens. This ensures that our generated text remains concise and focused. In addition, we have presence penalty and repetition penalty, which are designed to increase diversity in the suggestions. By penalizing the presence or repetition of certain tokens or patterns, we can encourage the model to produce more varied and engaging text. A good approach is, by the way, to first work with the default values of these parameters and only think about using one or a few of the mentioned parameters if necessary. Large language models, LLMs, have revolutionized the way we interact with computer systems, offering endless possibilities. One of the most impressive applications of LLMs is text generation, which can be used for various purposes such as generating articles, stories, and chatbot responses, allowing for vast creativity and automation. Another significant impact of LLMs is in language translation, breaking down language barriers and enabling global communication. Inspired by the concept of the Babelfish from Douglas Adams' novel, LLMs can translate texts from one language to another with incredible accuracy and efficiency, similar to the Babelfish's ability to translate languages in real time. Examples of LLMs in action include the DeepL translator, which can translate text with high accuracy, and ChatGPT, a chatbot that can understand and respond to questions in a natural way. As this technology continues to develop and refine, the possibilities are endless, and it will be exciting to see where this journey will take you. But nobody is forcing us to use language models only through the vendors' or integrators' web interfaces. We can also use these models programmatically through application programming interfaces in our own applications or scripts. I'd like to demonstrate this using the OpenAI API as an example. With this API, we can use the APIs of OpenAI, the company behind ChatGPT, but we can also use other language models if they are hosted with an OpenAI-compatible interface. For this hackathon, we are providing Llama 3 in 2 different sizes. I'll show you how we can use such models programmatically. OpenAI is a US-based software company researching AI since 2015. Initially nonprofit and open source, it founded a for-profit subsidiary, OpenAI Global, in 2019 with Microsoft as its largest investor. OpenAI developed the Generative Pre-trained Transformer, GPT technology, also known as generative AI. OpenAI's ChatGPT, an improved version of GPT 3.5, was released for free in November 2022 and gained massive attention with 1 million users registering in just 5 days. Despite limitations, its simplicity and user-friendly interface made it accessible to non-experts, sparking huge public interest. But much more interesting for this hackathon is the OpenAI API. Via this API, every developer can integrate AI models into apps, offering advanced language, audio, and vision capabilities. The API is provided in Python and JavaScript. We will focus on the chat completion part. But the API provides, beside text-to-text features, support for text-to-speech, speech-to-text, text-to-image, and moderation features as well. The OpenAI API is a kind of de facto standard for programmatically using language models, allowing developers to easily switch between models with a compatible API endpoint, providing a flexible and scalable way to integrate models into various applications. The code example shows how to use the OpenAI API to translate a text into English. Let us assume we want to translate the German sentence, Lübeck ist die Königin der Hanse, into English. This can be done using a prompt template. Our prompt template consists of a system and a user message. The system message in a chat model defines the context and instructions how the language model should process prompts. It typically contains a brief description of the goal, such as translate the following text into English, and can also define specific formatting or styles for the response. So, a system message is a kind of directive for the model how to generate the response. The user's message is the input the language model processes and responds to. It provides context and information for the model to generate an appropriate response. In our case, it's the text to be translated. Furthermore, there are AI messages. These are not shown in the example. However, AI messages are previously generated responses to previous user messages. In this way, you can use a sequence of system, user, and AI messages to create a conversation history as context and give the impression that an LLM remembers the course of the conversation. As we see, the OpenAI API offers a flexible and scalable solution to interact with large language models programmatically. Next challenge. You're new in town and have forgotten your travel guide, but you know Wikipedia, although the articles are always too long and kind of boring. However, Wikipedia articles in the local language are usually full of good information and free to use. After all, locals know their cities best. Let's take advantage of this and write a really short travel guide. We start with the last translation example and ask ourselves how we can adapt it. The problem is actually the same from the point of view of the language model. Text in, text out. We just need to change the prompts a bit and, of course, access the data on Wikipedia. Let's start with the database. We'll add 3 lines and simply use the Wikipedia API to get the information about our desired city. In our case, Lübeck. What else? If we were to execute the code shown here, however, the same thing as before would still happen. We would still translate the sentence, Lübeck is the queen of the Hanse. We must therefore still adjust our prompt and embed our information about Lübeck from Wikipedia into the prompt. But that's quite simple. We simply replace our previous system message, you translate texts into English, with summarized touristic facts from texts for English tourist guides, and embed the first 10,000 characters of our Wikipedia article about Lübeck into our user message. Why only 10,000 characters and not everything? Well, the context window of our language model is limited. Language models cannot process arbitrarily long texts. For this simple example, we're therefore limiting ourselves to the first 10,000 characters. It already works very well with this, and the farther you get into the back end of a specialized text, the more boring it becomes, as is well known. Done! And when we execute this now, we receive a touristic summary of Lübeck from our language model based on a Wikipedia article to learn the following about Lübeck. Lübeck's historic center is a UNESCO World Heritage Site since 1987 and boasts over 1,000 cultural monuments, featuring well-preserved medieval brick Gothic architecture and iconic landmarks like Lübeck Cathedral, Town Hall, and Holsten Gate. The city also offers 7 kilometers of Baltic Sea coastline, with attractions like the long sandy beach in Travemünde, the tall ship Passat, and the Brottener Steilufer steep coast. Additionally, Lübeck is renowned for its delicious marzipan, a sweet almond-based confectionery. That was astonishingly easy, don't you think? Awesome, we can now translate and generate travel guides. But is this enough to win a hackathon? Of course not. So, we'll have to cheat a little. But hey, it's a hackathon, so let's cheat and build a chatbot with Streamlit. We'll start with a Hello World app and end with a fully functional chatbot, exploring Streamlit's API and user experience capabilities along the way. By the end, you'll know how to build your own chatbot and maybe even create the next big thing in conversational AI. Streamlit is an open-source framework originally intended for data science and machine learning, allowing for collaborative and rapid prototyping and community-driven innovation. With Streamlit, you can build apps in minutes, making it a perfect match for hackathons. This amazing tool enables rapid development of data-driven applications, including data visualization, predictive modeling, and analytics, through its intuitive and flexible architecture. It supports Python and connects to various data sources and libraries, such as NumPy, Pandas, and scikit-learn. Moreover, Streamlit provides some chat features that are helpful for building chatbots. Let's build a simple Hello World app with Streamlit. This interactive app allows users to input their name, click a button, and receive a personalized greeting and celebratory balloons. The code is straightforward. Import Streamlit, set a title, create a text input and button, and display a greeting and balloons when the button is clicked. To run the app, save the code to a file and run it with Streamlit run helloworld.py. And that's it. You'll have a functional web app up and running in no time. Perfect for a hackathon. But this is still no chatbot, so we'll create a basic UI for user input and response display. This is where the magic happens, and our users will interact with our chatbot. We'll keep it simple, but you can always add more features and flair as you see fit. We then add the fun part, the conversational logic. This is where we bring our chatbot to life using Python. We'll write code that understands user input, processes it, and responds accordingly. It may seem daunting, but trust me, it's easier than you think. At the end, we will need less than 30 lines of code. So, let's get started and build something amazing together. Using Python and the Streamlit library enables us to create a user-friendly chat interface that is both aesthetically pleasing and highly functional. With this tool, users can ask questions, provide feedback, and engage in conversations with AI in a way that feels like they are chatting with a real person. The code on the left creates a chat UI, pictured on the right, where users input a prompt and the bot responds. The chat history is stored in st.sessionState and displayed on the page. Currently, the bot's response is hard-coded as an unintelligent answer, but we will replace this with a more sophisticated response generator. The interface stores and displays previous user prompts and bot responses, thanks to session states. Some helpful information to note is that st.sessionState is a dictionary-like object in Streamlit that allows you to store and retrieve small amounts of data that persist across user sessions and page interactions. Additionally, sc.chatInput creates a text input field that allows users to submit a message and returns the input text when the user presses enter. Meanwhile, st.chatMessage creates a chat bubble that displays the message and infers its visual style based on the provided role, either user or AI, distinguishing between user inputs and AI responses. A chatbot in under 30 lines of code sounds suspiciously simple. Let's check if that's really true. In the end, we only need to combine our LLM examples from before with the Streamlit UI. Let's start with the chat UI from before and add the missing code piece by piece. Of course, we need access to our large language model. We then have to prepare our prompt and set the behavior of the model with a system message. We do this with the session state, which contains the sequence of user and AI messages and begins with the system message but is not usually output in chatbots. And then we just need to replace the standard response with the generated response from a language model. To do this, as in the other examples, we simply call the completions feature using the OpenAI client and then stream the response to the user interface using WriteStream. Done. 30 lines of code and your chatbot is running. Just try it out and ask about the weather in Lübeck. You'll probably get an answer like this. But wait a minute, how can a language model have current weather data? We have programmed the bot together, so you know that the data has not been queried. So how can this work? Answer, not at all. In fact, the language model is just making it up, but sounds terribly confident about itself and the weather data. In Lübeck, the weather is usually not outstanding either, which means that 18 degrees Celsius is probably often correct, at least in summer. But that doesn't change the fact that the language model simply made it up. It seems quite likely that it is sometimes 18 degrees Celsius in Lübeck, but this does not necessarily have anything to do with the actual temperature. We will learn that LLMs should not be allowed to generate content completely freely, but only on the basis of a reliable context. We will get to know this in another screencast as retrieval augmented generation, but for now we are happy that our chatbot works. 30 amazing lines of code. Now we have a chatbot that runs locally, but to win a hackathon, everyone needs to be able to use this chatbot. So, how do we get this thing on the internet? Containerization allows us to package our application and its dependencies into a single self-contained container that can be run everywhere. With tools like Docker and Kubernetes, we can efficiently deploy our chatbot quickly and at scale. On your local machine or somewhere else, for instance, on one of our Kubernetes cluster, we are operating for these kind of purposes. However, let's explore how to do cloud-native deployments. Don't worry, we prepared something for you for this hackathon. Docker ensures consistent application runs across environments, eliminating works on my machine issues. It provides isolated, self-contained environments and highly portable images that can run on any Docker supporting system. Docker containers provide a self-contained environment for the application, including its dependencies. This means you can manage dependencies more easily and avoid conflicts between different applications, which can be a major pain point when working with large language models in Python. To build and run a chatbot image using Docker, we create a Docker file that serves as a blueprint. It specifies the base image, Python 3.11, sets the working directory to the app directory, adds the requirements file, installs packages with pip, adds the chatbot script, and sets the default command to run the chatbot with Streamlit. To build the image, we use the Docker build command, tagging it as chatbot. Once the image is built, we can run it using the Docker run command, mapping port 8501 on the host machine to port 8501 in the container. This allows us to access our chatbot from outside the container. But we can also deploy this container image in a Kubernetes environment, which we are providing for this hackathon. Kubernetes is an open-source container orchestration system that automates the deployment, scaling, and management of containerized applications. It allows you to deploy and manage distributed applications at scale, ensuring high availability, scalability, and flexibility. It automates deployment, scaling, and management of containers, ensures high availability and self-healing of containers, and supports enterprise-level applications with rolling updates and rollbacks. As Kubernetes itself is extremely extensive and complicated, we will not go into the details here. However, we provide all teams with a Kubernetes cluster on which they can deploy their containerized applications. The whole thing is already prepared. It is actually enough to know that the prepared deployment pipelines run against a Kubernetes cluster. I'd like to take a last moment to explain the repository that has been prepared for you. As you can see, it comes with an automated deployment pipeline, which means that whenever you commit code to the repository, a container of the chatbot is built, deployed to Kubernetes, and executed there. This process is fully automated, and it's ready for you to use. I want to mention that we have omitted the test and staging phases, as experience has shown that these are never really used in hackathons anyway. Let's take a look at how the repository is organized. You'll find that it's divided into several directories. There's the GitLab ci.yml file, which contains the deployment pipeline. I want to stress that you shouldn't touch this file. Then there's the deploy directory, which contains the necessary Kubernetes manifests for deployment. Again, please don't touch this directory. On the other hand, you're free to customize the chatbot directory, which is the app directory that includes the Python files and the Docker file. In the notebooks directory, you will find some Jupyter notebooks with examples of this presentation that demonstrate how to use large language models programmatically. Feel free to use our Jupyter Hub as well. By the way, we've embedded computer science students from the Lübeck University of Applied Sciences in each of your teams. They know these tools from their courses, so each team has some deployment experts among them. With that, I hope you're all set to get started with your project. I would like to take a moment to thank you all for your participation and your upcoming hard work during this hackathon. I wish you all the best for your hackathon endeavors and encourage you to stay in touch. Remember, our support team is here to help you whenever needed. Furthermore, I would like to take this opportunity to introduce you to our collaborative tools designed to help you take your projects to the next level. On our GitLab platform, you can work together with your teams, share code, and track progress in a seamless manner. You find your team repository there. Additionally, our Jupyter Hub platform offers interactive notebooks where you can experiment with individual code snippets and take your coding skills to new heights. As hackathon participants, you all have been granted access to these systems, and I encourage you to make the most of them. I look forward to seeing the amazing things you will achieve in the next days. So, code strong, Kira out.